It is important to understand the connection between using mixture models for classification and other procedures that are commonly used out there for classification. One example of those procedures that has a strong connection is linear discriminant analysis, and also, by the way, quadratic discriminant analysis. But let's start with linear discriminant analysis. And to illustrate that connection, let's start with a very simple mixture model. So let's start with a mixture model of the form f of x is equal to the sum from 1 to 2. So I'm going to be working only with two components of omega k 1 over square root 2 pi to the p, determinant of sigma to the minus 1/2 exp minus 1/2 x minus mu sub k transpose sigma inverse x minus mu sub k. So this is a two-component mixture with locations varying with the component, but the same variance covariance matrix for the two components that I have in the mixture. And let's think about how the procedure would look like if we were to do naive Bayes classification using this mixture. If I followed the unsupervised example that I had discussed before, the probability that I put observation I in class 1, say, I only have two classes, so it's easy. I can consider one of them, and the other one is just 1 minus the number that I get here. It's going to be equal, and I'm going to expand this in all its glory. It's going to be a little bit long. So it's going to be omega 1 exp 1 over square root 2 pi to the p, determinant of sigma to the minus 1/2 exp of minus 1/2 x minus mu k transpose sigma inverse x minus mu k. And in the denominator, we're going to have the same expression first. And then we're going to have omega 2, that is just 1 minus omega 1, but 2 pi to the p, determinant of sigma to the minus 1/2 x minus 1/2 x minus mu 2, sigma inverse x minus mu 2. Okay, and we know that the probability that xi belongs to class 1 is exactly the same expression, but replacing mu 1, which is what should be up here, replacing mu 1 with mu 2. So in the post-processing step, we are going to assign c sub I is equal to 1 if and only if the probability that xi belongs to class 1 is greater than the probability that xi belongs to class 2. And because the two expressions are the same in the denominator, the only thing that changes is the numerator, then this happens if and only if omega 1 over square root 2 pi to the p, determinant sigma to the minus 1/2, x minus 1/2, x minus mu 1 transpose sigma inverse x minus mu 1 is greater than omega 2 1 over square root 2 pi to the p, determinant of sigma to the minus 1/2 exp of minus 1/2 x minus mu 2 sigma inverse x minus mu 2. So probability of class 1 greater than probability of class 2 only if this quantity is greater than the same thing but evaluated for the second component in the mixture. So let's do a little bit of algebra, and let's try to simplify this expression a little bit. And we will see that that simplification leads to a very nice expression that matches exactly what you get out of linear discriminant analysis. So now we want to simplify this expression that corresponds to the situation where we're going to label an observation coming from class 1. And we want to make it much more compact. So a few things that we can observe. So one of them is we have 1 over square root 2 pi to the p on both sides. So we can cancel that. The other thing that we observe is that we have the determinant of the variance-covariance matrix on both sides. And because we're assuming that the two components have the same variance-covariance matrix, we can again just simplify both terms on either side. And the next thing that I'm going to do is I'm going to move all the omegas to one side and bring all the terms with the exponentials to the other side. If I do that, I'm going to end up on the left-hand side with the exponent of minus 1/2 x minus mu 1 transpose sigma inverse x minus mu 1. And then this term came to the other side in the denominator, but that just means that when it goes into the exponential, I need to change or to reverse signs. So it's going to be minus x minus mu 2 transpose sigma inverse x minus mu 2. So that's the expression once you move this to the denominator and combine the two exponentials. And this needs to be greater than omega 2 divided by omega 1. Now, some further simplifications, I can take the logarithm on both sides, and I can multiply by minus 2 on both sides, and I end up with an expression that looks like x minus mu 1 transpose sigma inverse x minus mu 1 minus x minus mu 2 transpose sigma inverse x minus mu 2 has to be greater than, less than, because I'm going to end up multiplying by a minus 2. So less than minus 2 log of omega 2 divided by omega 1. So now we have this difference of two quadratic forms needs to be less than a certain constant that depends on what are my prior weights for each one of the two components. Now, to finish simplifying this, we need to expand these two squares, which is pretty straightforward. So first we're going to have x sigma inverse x transpose sigma inverse x. This is just a square, so it's going to be 2 times x transpose sigma inverse mu1. And finally, mu1 transpose sigma inverse mu1. And then we need to subtract a similar expression for, but using mu2 for its terms. So it's going to be x transpose sigma inverse x. It's going to be plus, in this case, 2 x transpose sigma inverse mu2. And finally, again, minus mu2 transpose sigma inverse mu2. And all of this needs to be less than minus 2 log of omega 1. Omega 2 divided by omega 1. So you can see that the expressions are relatively straightforward, and one of the things that is very nice, and it's a consequence of having the same variance-covariance matrix for each one of the 2 components, is that now this quadratic term on the data, it's going to cancel out, and so we can just basically lump together a couple of terms. So we can write 2 times x transpose sigma inverse multiplied by mu2 minus mu1. So I'm taking this term and combining it with this term. So the term here and the term here. And then I'm going to say that this has to be less than minus 2 times log of omega 2 divided by omega 1. And I'm going to move these 2 terms to the right. So plus mu2 transpose sigma inverse mu2 minus mu1 transpose sigma inverse mu1. So this is actually quite a bit of simplification. And it's a very interesting one because you can think about this thing on the right-hand side. Just call this D for threshold. So this is just some threshold. And that threshold is basically computed based on the training data. So if I know the classes of some observations, I can get what the means for each one of the 2 classes are. I can estimate the common sigma, and I can estimate the relative frequencies. And with that, I can obtain a threshold from the training set. And I can think about this matrix product as some vector A. The form of this simplified expression is very interesting. You can see that the right-hand side, all this expression in the box, it's just a threshold that can be easily computed from the training set. We can estimate the weights, and we can estimate the mean and the common variance of the 2 components. And then this product of the variance covariance, or the inverse of the variance covariance matrix, times the difference of the means, corresponds to a vector A that can also be computed from the training set. So essentially, the decision of whether we classify an observation in class 1 or class 2 is going to depend on whether a linear combination, and that's what x transpose times A is, it's just a linear combination of the values of x. So whether this linear combination of the values of x is greater than a given threshold or not. In other words, what we're doing in a setting where we only have 2 variables, for example, x1 and x2, the linear combination of the entries is just a line on the plane. So this product just corresponds to a line. And by deciding whether we are above the line or below the line, we are just saying that one of the regions corresponds to class 2, and the other region corresponds to class 1. So this is the reason why the procedure is called linear discriminant analysis, because it uses a straight line to decide whether observations should be classified in class 1 and class 2. Now, there are some more interesting things that you can do. For example, you don't have to assume that the sigmas are the same. You could assume that the sigmas are different. If you were to do that, then you would be in a situation that is analogous to this one, with the main difference being that now these terms here wouldn't necessarily simplify. But then you can rearrange terms in such a way that now you're going to have a quadratic form of x being less than a certain threshold. And in that case, you're separating hyperplane. Instead of being a hyperplane or a line, it's going to be a quadratic form. And that is the reason why when you're working with kernels, you're doing naive Bayes, and you're working with kernels that have that are Gaussian and have different variance covariance matrices, you call the procedure quadratic discriminant analysis, because it uses a quadratic form, a parabola, or something like that, to separate the two classes that you're working with. The nice thing about thinking about these classification procedures in the context of mixture models is, again, thinking about ways in which you can generalize and address shortcomings of the procedure. It's clear that the main issue with classification procedures based on Gaussians is that data in the real world sometimes doesn't look like multivariate Gaussian distributions. So one possible extension is to, instead of considering the density, this piece here, to be a single Gaussian, you can kind of use mixtures a second time and borrow some ideas from when we did density estimation and say, well, I'm going to have a mixture, and each component of that mixture is in turn a second mixture that may have a few components, and that may allow for the shape of the clusters to be much more general, and that's what we call mixture discriminant analysis. As before, if you, instead of doing the EM algorithm and the simple maximum likelihood estimation that I described before, you instead use Bayesian estimators for your process, then you will have a Bayesian equivalent of linear discriminant analysis and quadratic discriminant analysis. So it is very useful to think about your statistical methods in the context of mixture models for the purpose of both generalizing and understanding the shortcomings of what you're doing.